Look how far we've come. We're almost there. We're almost there. 300 years ago, like 1700. So we're right. We're not quite. We're right in there. Right in there. Right about where telescopes were invented, but not used quite yet. Not in the course, at least. Let's do our checklist. Remember, review is key. I know there's a glare there, but I think you'll survive on that one. Let's just go like this and let's check it off. Let's check it off. And then review. Go back through it all. I'm not going to do it for you this time. I'm tired of me doing that. What do we got? All right, we got our dots. We've got our dots. Pictures of stars and planets and moon and sun, one after another. Figuring out when, time, so how quickly are they moving? Quickly, what do we measure? Not separation, but angular separation. That's why those angles are so key. And who's going to figure it out for us? Well, Kepler, a German mathematician, astronomer, and astrologer. And a lot of these folks, the church, people were wondering. So astrology is interesting, right? But you got to be able to test it. Remember, they still didn't know if it was heliocentric or geocentric. They didn't have the modern tools we have. And so when you test, it's actually pretty easy. But they were doing what they did. And so I've heard people say, well, back in the day, people thought astrology, and say, yeah, well, back in the day, we evolved knowledge. I know now today they would obviously, it's about the evidence, right? So it's about not opinion. Anyway, we're going on to Kepler for this video, and we're going to see his three laws. I call them K1, K2, and K3. Kepler's First Law, Keplers Second Law, Keplers Third Law. Getting a little cluttered over there, so let me go there. I want to say that at that time, Galileo was over in Italy, and a telescope had already been invented, not by Galileo. We'll talk about that. So he was doing his thing. We're going to see that next. And Kepler was doing his thing around 1600. So we've gone past the Renaissance, and then we're going to get ourselves to modern science real quickly. So this is Leonardo da Vinci, and he was an amazing inventor. He thought way ahead. I mean, how could he think? He died when he was like 60 or so, something like that. And so did a lot of these folks. Kepler did. But how could he figure out that there would be electric guitars and a Stratocaster, no less, which you'll see in chapter 5. Okay, he didn't do the guitar. But we were thinking about things. Art, right? Here it is. Art, science, being human, right? Being full humans. Let's bring that back into our education system, shall we? Wonder about these things, but have the honesty to measure it. Let's do it. Let's see what you can figure out. It's hard work, so, let the other guy do it. Or gal, certainly, women, let the other people do it. Whatever. You do your thing. Whatever it is. If you're making music, hey, then we're listening to it, well, crank away at some numbers, whatever the case. So we've got this, am I going? Okay, I'm still going, okay. So let's do Kepler. All right. So what did Kepler find from those dots? All right. Let's zoom in, don't look too much. He figured out from Tycho Brahe's dots, from his observation maps, that all planets, including Earth, what? Earth is moving? It doesn't feel like Earth is moving. Sorry, Tycho, you're not quite right there. It wasn't the way you thought it was, but your dots tell us that it is heliocentric. They move around or orbit sun. And they do it in 3 common ways. So already we got, wow, it's not only is it heliocentric though, the glory's in the details. He didn't say it's just heliocentric, which is cool. It turns out it's not actually, sun is not at the center, he found out. There's 3 laws. There's 3 ways that every planet moves. But he didn't know why they did that. And he won't know. Let me give you a preview of that. Newton, okay, 3.8, Isaac Newton. All right, so we don't know that yet. How do they move? We're going to talk about that. As we go over here, I'm going to show you something over here. You might see those shapes up there, right? Let's talk about this. Okay. They move around the sun. So in a circle, well, if it was a circle, put kind of one on top of the other. Well, these are funky magnets. Let me do that and that for now. Put that off to the side. And if they moved around the circle, then the sun would be, say, here. And a planet might move around a boring circle. I won't make it too big, so I shortened it a little bit. And the way I could do that is just attach a string and have this line be the same distance away. If this was a planet, this is a planet orbit. Now, this would be seen from space. You never see this. You've never seen it, right? Not with your naked eye, not with your own eyes. That's a circle, good enough. Something like that, right? So we're imagining this is seen from space, and all they could do is draw it and try to figure out what must be happening so that we see what we see. And so people thought circles. Remember, Copernicus said circles, perfect circles. Kepler said, nah, it's heliocentric in a rough term. In other words, we orbit sun, but sun isn't at the center. The way it works is this. Let's check out another shape. Now, you know, if you look at lips, they kind of go like this, right? They're not like a circle. They go like an oval. But this is technically not, this is a technical shape, and it's called ellipse, like ellipse. So an ellipse is like this. How do you make an ellipse? Well, you can stretch it out. So you don't really have a center. You kind of have a center, but you stretch these 2 points out here, the foci. Got this in the book, so I'm just going to say this kind of quickly and just to give you a sense. We're going to draw this conclusion. There's going to be something cool about this, though, that I want to point out. I wonder if I can pin that down a little bit more and make it a little stronger. That's the wrong magnet. Actually, it's not what I want, but that'll have to do. Oh, I got it. Don't worry. Yes. Let's get rid of these. Neodymium, right? Don't snap them. Magnets, what are these things? They've been known about for a long time too. Couldn't know about it until, really understand it until the 1800s. We're getting there. Oops, flip it. Oh, yes. All right, cool. So not a circle, but what's that shape? Stretch it out a little bit. That is a stretched out circle. That is ellipse. Oh, I love it. Up and over. Okay. Got tied up. No, that's an ellipse. And then I've got 2 points here. And what if you stretch it out even more? Maybe I should have started. If I stretch it out even more, what do I get? I get that. Okay, so that's the shape called an ellipse. Now what we're getting at here is that Kepler found, by looking at those dots, which is really challenging, give it to a grad student, it's going to be challenged. It's hard to do. He said that sun wasn't actually at the center. It's not heliocentric. Sun was at one of these points. And nothing was over there. There's no string in space. But where is sun? I mean, how stretched out is remember, this is the path of a planet. Mars, say, Jupiter, Saturn, right? Earth. Earth's a planet, yeah, he said, including Earth. Venus, Mercury. They all go around Sun. But where is Sun? And how stretched out is that orbit? It's not a circle. It's not that perfect circle. How stretched out? Well, Sun is at one of these places, maybe here. And there's nothing over here. For some reason, we go around. We don't know why. Again, we say, what? What is going on? What is going on? And so one way to characterize this, because you're going to, if you get a sense of this, just a little sense, then I'm going to show you something and you'll understand why books lie to you, including my book. But I pointed out the pictures are misleading. Watch. All right. So we talk about how different someone is by their being eccentric, eccentricity, and that makes them a good artist and interesting to talk with and all kinds of things. So eccentricity, let me write this. How stretched out that ellipse is in the book, how stretched out it is, I'm going to write it this way. We've got the eccentricity and E, and there's a math equation, and again, he did it very mathematically. And then there's the shape of roughly what it looks like. Now this is going to lead to some cool ahas. So if the shape is a circle, that's very normal. It's not stretched out. Not very interesting. I don't know. We give it a number 0. E is equal to 0. The most I could stretch this is that. And that would be a line, which looks like what number? Number 1. A line, or a line between those points. That's the most stretched out. So anything else, as I go from circle to more and more stretched out, is given a number, mathematically, you don't have to worry about that, between 0 and 1. So let's just go, you could do anything, we'll use decimals. 0.1 is not, it's almost a circle, right? In fact, if you draw that, you'd say, oh, nice circle. 0.2, 0.3, oh, I'm not leaving myself room, 0.9. If it's 0.9, it's going to be really stretched out, right? So let's see what those orbits are. How can I see? Internet. How can we have internet? Because these folks started working this stuff out. Where am I? Yeah, let's do that. And then let's do that. Check this out. Let's go to the internet. There's pictures on the board. Are they accurate? Oh, I know that. Polaris, the North Star. What have we got? Leonardo da Vinci. Let's check. So we talk about the Renaissance, the renewal, right? 1452, died at age 67. Yeah, too young. Brilliant, right? Brilliant. Art, science. See, look. Where is it? Mona Lisa, right? There's that picture. So, really. Okay, polymath. Anyway, so fun to look at these folks. And then, then you got Brahe coming on the scene, trying to settle that tie. Then he goes and dies. I think he was 61. I don't know something. No, he was 54, right? And then I think Kepler dies when he's 61. That's like way too early, man. Passes his dots on. Then you got Kepler, this guy here. And I think it's fun to look at the stories and see the thinking and see the evolution of thinking. Nonetheless, let's go over here. I want to find, happened to have bookmarked it. What chapter are we? 3. What do I want? Data table for planets. There are a variety of ones. Really? There it is. Okay. This one's nicely laid out, so I'm going to do this. Okay. Check out those planets. See what you see. Now, what am I going to look at? What I'm looking at here are the eccentricity, orbital eccentricities. How stretched out are they? Remember, a 1 is totally stretched out a line. A 0 is not stretched out a circle. 0.1 you can't even tell. I'm going to go to Earth. It's not even 0.1. It's so close to a circle, and this is going to tell us something in chapter 4 about seasons. It's so close to a circle, so when we draw it really stretched out, we're exaggerating the point. Remember, 0.1 looks like a circle. This is 0.016. This is almost perfect circle, but it's a little stretched out. It's not even 0.1, not even 0.1, not even 0.1, not even 0.1, not even 0.1. Really close to a circle. And how did Kepler figure out that it wasn't a circle? Boy, he looked really closely at those dots. Mercury 0.2, it's a little more stretched out. There's reasons for that and clues. Very interesting thing about that. Nonetheless, there's the eccentricity. Okay, so it's I mean, come on our list, we're talking about in here, it's so close to a circle, but I'm still going to draw it exaggerated now that I've excused myself from being accurate there. So Kepler's first law, I'm not going to write out the words, they're in the book, says this, K1, Kepler's first law. How do planets, now I could do any planet, but I think Earth is interesting, right? You can do Mercury, and Mars, etc. And how do they move? Well, Earth is moving around on something very close to a circle. I'll show you how. And here it is, coming around. And so I'll draw it at a couple of positions. And I'm going to ask you to guess, pause and guess. And if you engage in that, you will literally change the structure of your brain. It's how the brain works. If you cram stuff, it comes and goes. That's not how the brain learns. So you'll always feel like you didn't learn anything because you didn't. It didn't wire the brain. Anyway, so I'm going to have Earth going around this way. Sun loosely at the center, heliocentric, but not really. Sun off to one of those points, and it's going around. Why? We don't know. We're just saying. He's just saying the dots tell me this. This is seen from space, right? We live on here. Now, this is the farthest that Earth would be from Sun, and there's a name for that. It's away, so think of it, APH, but we'd say aphelion. I don't know anyone that says aphelion. Think away from Sun. Okay? And we'll talk about what day you might think that is. On what day of the year do you think that is? I know what I would guess. Comes around, and then here it's the closest to Sun, Earth, our planet. It's perilously close. Okay, Dr. Adrian Kuhl at San Francisco State University, astronomer, I'm stealing from you. But that's because your name is unfair. It's Dr. Kuhl. I mean, seriously, that's her name. It's not fair. Anyway, so she says it's perilously close. Oh, I like that. Perihelion. I don't know, however you remember it. So it gets closer and then farther, but you know it's really not that much closer. How much closer, how much farther? Well, we'll check it out. Well, here's a clue. On what day? What do you guess? Did you guess? Make a guess. Think about it. Remember stuff. Pause. Shut me up. I would guess the winter solstice. And I'd be so wrong. I would guess the summer solstice. I would be so wrong. In fact, we're farthest from the sun. This is fun to tell you. On about July 4th. It's not a solstice, it's not an equinox, and it's not even winter. Well, it is winter in the southern hemisphere. Interesting. It's only summer in the northern hemisphere. And over here, about 6 months later, right? January 4th or January 1st, it's close enough. So when it's come down, like January 1st, yay, Happy New Year. Hey, we're the closest to sun today. Hey, you've had a little bit too much of that punch. No, we are. How can that be? It's winter, not in the southern hemisphere, it's summer. Hey, happy 4th of July, Independence Day. Hey, we're farthest from sun. Farthest? You've had too much of that punch. No. It's not exactly, it could be a little different the 4th, but about that. Wait a minute. How can that be? Well, it can be because on average, remember we're 93 million miles away, 1 AU. And here plus 1 or 1.5, if you want to be picky about it. 93 million miles minus 1.5. So, and 1.5 million miles, yeah, it's a lot, but not compared to 93, and it just doesn't dictate the seasons. It's really close to a circle. I just can't draw it because you go, wow, it looks like a circle. No, it's not exact. Remember, it got Copernicus in trouble? Because perfect circles, it's not perfect. At the same time, Galileo was going, yeah, probably perfect circles. But anyway, so the other thing that begs, I got 2 questions for you, and then we're done with this one. This is maybe the most complicated. So, number 1, where are the solstices? What's going around this way? July, so it's somewhere in there, right? Around June 20th, 21st, some places say 22nd, that's not as much, whatever. Summer solstice. And we'll see that it's tilted towards sun. We're going to get that. It's chapter 4. Shh, we don't know that yet. And then it comes around. Before January, we've got the winter solstice. Around December 20th, 21st, whatever. Winter solstice. So this doesn't even happen on the solstices, nor on the equinoxes, because those are opposite too. So it's an interesting thing. What gives us our seasons? Well, you don't know because you haven't read chapter 4. So chapter 4 will tell us that. This is all we knew. He didn't say why. I just know that sun is basically at the center. It's basically heliocentric, but not exactly at the center. It's a very mathematical shape, and planets move this way. And if I put this math to these dots, they match. Wow. And this is crazy. But it's very close to a circle. Okay? They move around. Now the other thing, if you think about it, it doesn't feel like we're moving, but there's something else it really doesn't feel like. Keplers Second Law. Our planet goes faster and faster, and then it goes slower and slower. Increases speed, decreases speed. Planets increase speed as they approach sun. So, if this is going, whatever planet that is, and it includes Earth, it's going to be increasing speed faster and faster. And as it moves away, it's going to be decreasing speed. And this is what I want people to be able to tell me. Keplers Second Law says this. In fact, it decreases speed until it's a short arrow now, slowest at what? What do we call that position? Slowest when it's away at helium. What day? Remember, it doesn't make sense. So it's far away, so it should be colder, but it's actually warmer July in the north. On July 4th-ish. So sun is going slowest on July 4th. That's why everybody's kind of chill, relaxing and everything. That's why. That's kind of like astrology, isn't it? And then it's coming around and it whips around here. What? It's going the fastest. I'm going to show you something here. So fastest at what do we call that? Perilously close, Professor Poole. At perihelion. What day? Is it the solstice, equinox? No. Remember? July 4th, January 4th. Just loosely so you can remember it. It's close, right in there. Okay. So where are we today? I mean, where are we? We go back on this other one. Where are we in our path? If this is, remember, it should be hot, but it's cold. January, say 4. Oh, yeah, you can say January 1. That works. July 4. Where are you today? What's your date? If you're in fall, approaching thing, and you're going over here, going faster and faster. So when I'm making this video, it's fall, and it's going faster, Earth is going faster. It's a very tiny thing, and it's incredible what Kepler could figure out. But only because Brahe did such a good job. And then we're going to go slower and slower, and faster, but it's very minor. But there's a very particular way. He didn't just figure out this. The way that you'll usually see Kepler's law stated is planets move so as to sweep out equal area in equal time. And students go, that doesn't mean anything to me. I don't know what you just said. That's a on the certainty scale. So, but let me show you what that means. This is what I want people to know. But what that means is if you're going slow here, then say a month, if this is Earth, some period of time, if you're going slowly, then you're not going to go very far. And in that same amount of time, if you're going fast, you're going to go a lot farther. Now notice, if you order a piece of pizza and it's sliced like that and you're hungry and you're looking for the biggest slice, don't worry about it. Because those slices have the same amount of pizza, the same area, they weigh the same amount. And planets move this way. Why, Kepler? I don't know. Why do you say it does? Are you just guessing? Is that your opinion? No. Well, how do those dots tell you that? Well, here, I'll show you. People didn't get it. They didn't get this right away. This was hard to understand. And then you're asking me to change my whole worldview where Earth is not moving and everything's going around me and we're special and, we're the center of attention. They didn't get that. What was his third law? Whew. His third law was this. Ready? Review. First law, sun's not actually at the center, or planets don't orbit in circles, but they're very close to circles. So it can be a little closer, a little farther. When it comes to Earth, we're a little closer around January. You can say January 1st. That's kind of cool, easy to remember, or January 4th, whatever. And then we're a little farther, July 4th. Not even the solstices. Cool. And we're actually changing speed as we orbit. But since it's so close to a circle, that change is not that much. And if you want to look that up, you can. But let me go with now over here. Let me do Kepler's third over here, and we're done. You want to get into the math of it? Well, go for it. Kind of interesting, but there's other things to do too. So And we've continued to look. Why this happens, we have to get to the end of the chapter. This is what he found from the dots. And one key to learning too is, this is a hard one for people. Our tendency is to be kind of weak, like, well, I don't fully get it, so I don't get it. I'm not comfortable. You have to be comfortable not knowing, and you have to be comfortable continuing to ask, okay, well, I know this. I do know that. I know I don't know it completely, but I know this. And so you just work forward and not have that be a barrier. Well, I don't get it. But you get this. But you get that this, Brahe didn't know at all. It's like, I don't know, it's a tie. I think it's probably something like this. Let me see if I can work this out. Let me measure it and see if I can validate it or what's going on. Kepler says it's like this. And then you still say, well, why? And then we're going to get Newton to tell us why. And then we're going to see that that's really, really good, but not perfect. And so you can keep digging. You got to let go of that sort of perfect, absolute knowledge and just keep inching forward. It's a way of thinking, isn't it? And so Kepler's third law, look at this. It's like a nose. Anyway, whatever. It's art. All right, Kepler's third law. What did he find out? What's true? Just from observation. Took him a while to get this. I'm going to read it. To go around or orbit sun once. I'm going to show it to you on that data table. To go around, which means orbit is another way to say it. To go around sun once. And that's called the, I guess I'll say it here, orbital period, or that planet's year. My silly drawing. That planet, a Mars year, how long is that? A Mercury year, how long is that to go around once? Here's the thing. Planets, I'll say, you could look at closer or farther. I'll just say planets farther from sun. Take longer because of two reasons. Take longer because why do you think? Farther from sun and also let's draw it. But what does that mean? Now I'm going to draw it, sometimes I'll draw it like circles because it's really close to a circle. And so when I draw this really stretched out picture, that's just to exaggerate the point. When you see that online pretty much everywhere are books, you've seen that really planets go in near circles and it's amazing you could figure out that it wasn't a circle. Let's try to sketch this and see what this looks like here a little bit. So I'm going to draw sun. Now you have quite a bit of understanding, right? You do understand this. You know this, just like he knew this. So I'm going to just make planet A. I could do A, B, and C. Let me just do A, B, and C. It doesn't matter. It could be A, B, and C. Maybe B is Earth, or it doesn't matter. And we know they go around in nearly circles, whatever. There's A orbiting, B orbiting. It's really an ellipse, so it goes a little faster, a little slower, but a little closer, whatever, something like that. And C. All right. So why would it, if you're running a race to get around once, why does A have an advantage? Why does C take longer? Because farther from Sun, it's a longer way around, right? Longer distance around. So yeah, I'd expect it to take longer, and indeed it does. So there's that. And here's the thing that is not clear, because when he measured, and this is hard, because it's not like you see something go around you and you measure how long it takes, and that could be years or whatever it takes. But you're also moving. How do you figure out your motion and their motion looking at Brahe's dots? I mean, if you're impressed, that's all we kind of need. And then we say, well, this is what he found out. He said, the farther out a planet is, the slower it travels, slower speed. The farther out, I said I wasn't going to write it, but the farther out a planet is from Sun, the slower speed it moves. So you got long, it's like, okay, it's a race, go! And what do you have? Maybe A is motivated because he sees, I got the short track. B, not as fast. C, not as fast. Forget about it. Like, who are you putting your lunch money on? I keep my lunch money. I want my lunch. But, all right, that's the way he found it. Now there's an equation that relates it. I think I included it in the book. I teetered on it because we're not doing it's descriptive, but there is an equation. That's the amazing thing. Wow, he figured out an equation that if you draw he never saw this. He never saw this. He just saw those pictures of dots, right? But from their angular separation, right? He said this must be what it must look like for aliens or gods. That must be what's going on. And he did an equation, and it fit. And so now you know why they have a longer year. Because it's longer year if it's farther out. Now you know why, because it's farther around, and they go slower. And you say, but I don't know why that is. And I say, I know. Remember what I said? Just because you can't think too far ahead, you'll never get there. It's in life, you think you're going to go here, and you end up changing your major. Join the crowd. I did. I was going into engineering. This is cool too. It's all related. All right, cool. That's his third law. And that's, I think, all I have to say about that. Oh, no, let me show you something. See, I did that last time. All right, here we go. Let's show. Let's see. Yes, almost done. Almost done with Kepler. Huge step. We are almost done with this. Set it up. Look at this. What do I want? Orbital period. There's eccentricity period right above it. Right there. You see it? Let's see if I can go right. Sound effects. All right, good. Compared to Earth. So Earth is 1. So compared to Earth, this is the order of the planets from Sun. So you can do distance from Sun, and we're going to study that farther and farther out. And as you get farther and farther out, this takes, well, really 88 days, about 3 months. 88 days, about 3 months. So that's one season for Earth. As we go from one season to the next, from solstice to equinox, or equinox to solstice, Mercury's gone around once. This guy is about 8 months. So that's about 3 Earth months, about 8 Earth months, about 12 Earth months. Mars is about 2 years. We're going to see him play with that. That's crazy. 2 years to get around. So we go around once. If Mars is here, which it is right now, it's kind of close to that. If we go around once, Mars is over here. You want to come home and you went to Mars, you got to wait. About 12 years for Jupiter. So when you turn 24 years old, you're like, hey, I'm two Jupiter years old. When you turn 30, round it off, you can go, oh, I'm 1 Saturn year old. Oh, and my heart's almost beat 1 billion times too. 30, 32 heartbeats, 1 billion heartbeats. 32 seconds is about, 1 billion seconds is about 32 years, right? So anyway, 30. So in your lifetime, how many times has Jupiter gone around? In your lifetime, has Saturn even gone around? In your lifetime, right? See, a lot of these folks died well before that. 84 years, that's kind of a human lifetime now. And more people are getting there with healthcare, et cetera. Why? Thanks to these folks for laying this foundation. It's relevant, and it's the foundation, and we give appreciation to these people. Now, personally, I'd like to live at least a Neptune year. So I really want the science to continue, and I want some of you or people that you know, and you can work as the whatever, grant writer or designer or whatever you do for NASA. You're still part of the team. So whatever you do, if you work at Trader Joe's, you're part of the team. I love people that work there. In fact, some of my students work there. So let's try to live one Neptune year. I got stuff to do. And how are we going to do that? Well, we're going to take another step. But remember that at the time, while Kepler was doing this and figuring this out, and then when he did, it was like, what did he do? I don't know. Does that really? I don't know. No one's reading it, right? Well, at that same time, Galileo was working. Let's see what he found and what he did and what got him in trouble. And we're almost done.